But I think we'll get started. Welcome. I'm Matt Schuerger with ESIG, and welcome to the first session of the afternoon, Power System Impacts of Rapid Electrification. So clearly, clean electricity is the linchpin to a net zero economy. With an increasingly decarbonized grid, there's tons of opportunities for electrification that benefits customers. Many jurisdictions have seen relatively flat load growth, minimal load growth over the last couple of decade or two. But now with the increase of electrification coming upon us, now starting to see pretty significant load growth, which we've been hearing about in other sessions. So, I think when we look at decarbonizing by 2050, most scenarios, if not all, show at least doubling electricity production delivery, if not moving towards tripling. So this panel will really kind of dig into what are some of those impacts of rapid electrification. We'll start off with two presentations from leading utilities that are really leading the way in planning for rapid electrification. We'll move into a presentation on some specific tools and approaches to dealing with electrification, and then finish up with a fourth presentation that really looks at a specific example, a cautionary tale, if you will, about some of the impacts of electrification. So we'll, as other sessions have, we'll go through our presentations and then take questions at the end, but we really want to engage everybody in questions and discussion. So please be jotting down your questions as we go through the presentations, so that we can have a robust discussion as we get through them. So with that, I want to introduce our first speaker, Jun Wen, who is the TEP initiative lead, as well as a principal advisor in DSO strategy and implementation with Southern California Edison.
All right, good afternoon. So my name is Jun. Pleasure to be here. I lead SCE's transportation electrification grid readiness activities. So the magnitude and pace of the load growth will be unprecedented, as we heard from multiple sessions already. At SCE, we are already experiencing this load impacts today, and we'll only expect more. I can tell you the most question that I've heard most in the past 2 years is there enough grid capacity? So for this presentation, I'm going to briefly touch on our recent countdown to 2045 analysis. And most importantly, I'm going to focus on some of the challenges that we're already seeing today, and how SCE is readying the grid for both long-term and short-term. So a little bit about who we are. SCE, Southern California Edison, we are one of the largest investment utility in the nation. We provide power to 15 million people, over 50,000 square miles in the coastal, central, and the southern part of California. So California is one of the states that has the most aggressive climate change goals. So we are targeting to have a net zero GHG emission economic-wide by 2045. Since 2017, SCE has published a series white paper really laying out our vision and the cross-sector collaboration that is essential to achieve those energy targets. So some of this white paper is more blueprinting and really leading our way to 2030, 2045. Some of the paper is really focused on how the grid should be modernized and transformed to really enable this clean energy transition. And the gap white paper is really about a policy assessment. So the recent countdown to 2045 is a data-driven analysis, and it's a refresh our Pathway 2045 analysis we had back in 2019. The reason that we did a refresh on this study is because AB 1279, which is really requiring a deeper direct emission target, which is 85% by an earlier date than the original 2050. So there are some great learnings from this analysis. So the analysis starts with the economic-wide GHG emission model, really determining the most feasible and economic mechanism to really achieve this 2045 target across the sector. And from there, we did a demand forecast. The analysis concluded that by 2045, 90% of the vehicle will be electrified, and building electrification, that's about 95%. And with all the load total, we will be seeing over 80% of the electrical demand in comparison to today. With such a huge load increase in the next 2 decades, that means, we just need to build our infrastructure much faster. So as you can see on the left chart here, in order to identify 100 plus gigawatt of new resources by 2045, the transmission will need to be built up to 4 times faster than the pre-2022 time. And on the right-hand side, that's an assessment of our distribution system. As you can see here, in 2045, the distribution system will be 24.5% larger. So today we have about 800 substation, 4,600 circuit. And by 2045, we will expect that system to be expanded 25% larger. And as you can see the chart here, the first 10 years, the need of substation is still manageable. However, in the second 10 years, the speed of escalating this infrastructure development is going to be tremendous, right? It's up to 7 to 10 times. So that means we probably need to think about our design differently. For example, looking at a higher voltage distribution circuits, looking at more compact substation with less land requirement. So those are the long-term requirements we're starting to looking and exploring internally. So now pulling back to some of the challenges we're already seeing today. So as you can see the chart here, this is the actual received transportation electrification application today. So 2 things I want to point out from this chart is one is really on the left-hand side from 2021 to 2024, but definitely see exponential growth. It's not linear, that's exponential growth. Some of the chart I didn't show here, but I will just verbally voice over, is we're starting to see a very steady trend on the application we receive every month. So in 2022, we're probably still seeing 10 projects per month. Then 2023, probably 20, 30 projects per month. And this year, we have been seeing a steady 40 projects per month. And we're only, the counting here, I only include the project that's larger than 500 kW. There are much more smaller projects, that's not including this analysis. So back in April, we're even seeing 60 projects just in that 1 month. So the other point I want to make on this chart is every year we're planning for the 10 years. However, if you can look at the 2025 to 2033, honestly, there's very limited visibility to what customer is planning for. So the challenges for planning those very large load coming to our system, but seeking for very quick service has some challenges. One is there's really large uncertainty in where and when the EV charging load will materialize. And for the first time ever, those load is not stationary, it's going to move around. So even putting more challenges on how we forecast that demand. On the other hand side, all those load, they're looking for very quick service. Their lead time coming to us is only about 1 to 2 years. However, those load can be very large, right? For example, a 30 semi trucks, that's about adding 5 megawatt load to the system. If you think about maybe a synergy to use, it's like adding a small neighborhood just on a very small footprint. And imagine like in the past, those projects can take years, but now they're already taking about 1 to 2 years to build. And those large demand can easily trigger some of the capacity upgrade, which can take years to build. For example, if they trigger, a substation build projects that requires licensing permitting, that can really take a number of years. So the challenge is really how we can plan for the infrastructure of this new large uncertain demand to ensure the timely energization they're looking for, but still maintaining an affordable rate, not overbuild, not underbuild. So that's really the challenge we're dealing with now. So to really mitigate this chicken egg dilemma issue, we have come up with a proactive planning, which is called T-equal readiness. So a little bit maybe context before I get into the tiger. So every year we do this 10-year planning. So we look out 10 years and we plan for our distribution, subtransmission, and the transmission system to meet the anticipated DER and demand growth. So in California, the 3 investment utility companies are required to use a state forecast, which is CCIPER forecast. Each utility will then take that forecast to disaggregate to the circuit for distribution planning. Now, we've observed some challenges for that top-down disaggregation approach, because with top-down, you're probably getting little here and there, maybe 0.1 megawatt on the circuit. However, in reality, we're really seeing some very big projects, 5 megawatt, 10 megawatt. We're seeing 30, 40 megawatt projects on the EV really coming to the distribution system. So in order to mitigate this challenge, we have been taking proactive steps, really come up with first of the kind at the time to do a tiger study. So beyond the normal annual top-down study, in this analysis, we were able to really conduct a location selection analysis, identify some of the hotspots. The hotspots is determined by a combination of T growth and also the limitation of the grid capacity. So in those locations, we were able to augment on the top-down forecast using the bottom-up scenarios. As you can see the graph, it's really, the select location is really from the Port of Long Beach, Port of Long LA, really through the I-710 corridor, going through the Guzman and to the Inland Empire area. So the locations really focus on the free corridors, truck stops, distribution centers. As part of the study, we identified additional $1 billion grid investment that is really needed to start those least regrets investment in the hot spot locations. So the reason taking that approach really prioritizing area is really to minimize the risk, because any project in those locations move forward, we will be still providing the timely energy service, but not creating risk for the load is not showing up. What I also want to mention is we having through the 2 years really partnering with the commission and also CEC, and conducted some of the locational assessments through the free infrastructure, free corridor assessment. And this year, CPUC actually released a white paper through the high DER OIR proceeding. They introduced a terminology called a pending load. The tiger is essentially a form of pending load. So the pending load refers to the load. They haven't really submit their application yet, but we do anticipate they're coming. So in this case, we will actually working with PUC and expanding the pending load, refining the methodology, and the pending load will also include other non-EV load, for example, approve the city plans, residential development, and also data center load. So now moving on to the near term. So we also have the power service availability initiative. Regardless how well we do the forecast, there will be always cases where customer come to us, pretty large load and request to be connected in 1 or 2 years. So the PSA initiative is really looking at, how we can improve our internal processes to streamline the interconnection. We're also engaging fleet operators to better understand their plan and also improve our capability to forecast and assess the impact. And also leveraging new solutions for the grid infrastructure. So there are 4 pillars under this initiative. The first initiative is foundational process improvement. We're really looking at streamlining some of our engineering and also field scheduling, staffing, resources, processes, and also enhancing some of our intake tool to make more transparency to the customer on where their project is at. The grid capacity map is also part of the foundational process improvement. The second large pillar is really on the forecasting analysis. So apparently we're moving from circuit level to structure level, but in addition, most importantly, we're really starting to providing a lot of engagement with the communities, with fleet operators, and then really trying to bring that insight to inform our pending load assumptions. And then speaking of the great infrastructure, we're looking at both long-term and short-term. So the short-term, we're looking temporary bridging solutions, and longer-term, we're looking at different great architecture design, right? For example, distribution automation. Like, do we need to even segment our circuits more to bring additional resiliency, reliability to the customer? And long-term process requirement, we're looking to further streamlining the licensing permitting process with the state. We're also working with the cities, communities to do master planning. So I just want to highlight a few examples out of the PSA. So the first one to highlight is the grid capacity maps. We think that's a great tool to really help the customer to self-serve themselves. We're getting a lot of speculative requests. Customer doesn't know where they want to go. So we definitely see a lot of customer, maybe they're just looking one project, but they may be submitting 20 requests. So on this portal, if you click on that every circuit, you will be able to see the available circuit and substation capacity. And the capacity map is refreshed on a daily basis. So whenever we have a project that is confirmed on that circuit, the capacity will actually be taken. So the customer will get a timely view of what's remaining available. So the customer also has the option to do a bulk download and using Xcel to just sort the available capacity. That's really helpful for the customer who has a flexibility to do the site selection. So we'll continue enhancing this, and we probably will bring that down to the nodal level and bring the forecast view instead of as-is view. So by having this tool, I want to say, several benefits. One is really helping us to optimize the existing grid asset utilization by directing the customer to the available capacity location, and also kind of helping to really saving on some of the labor resources on the engineering side to minimize the speculative request. So the next area I wanted to highlight is the forecasting and analysis. So we have been conducting quite extensive fleet operating engagement last year, 20 plus. Some of them are targeted, like for example, to the cities, telecom or schools, and some are general, like with broader audience. The reason for this outreach is one, the fleet customer, they don't necessarily in the past deal with utility. So they don't necessarily know the utility process. So this workshop will really help them starting from day one, including how to size their charging infrastructure all the way to the project and the vision. So we have dedicated staff really supporting those fleet customer needs. And most importantly, we also are trying to really encourage the fleet operators to come to SC early. There are two types of early engagement messaging we're sending to the fleet customer. One is really for the long-term planning. Some of the fleet operators always think SC knows everything, which is not true. We know where the power is consumed. We don't necessarily know how many vehicles they have and where they park. So we're really encouraging them to come and provide those information, even if they don't have a plan. Even help letting us know that information will help us to validate some of the data we have. The other early engagement is really for the service connection. So we're really trying to provide a guidance on some of the project sizing and the lead time they would be expecting. So that kind of help them to set the right expectation to really come to us and helping them to work through the entire energization request. In addition to the fleet operator, we are also trying to do the communicate engagement. So that's really communicating with the city, communicating with the communities, and also encouraging them to partner with us to make sure their plans can be incorporated into our annual capacity planning. And I showed the box here is because that's really the challenge we're dealing with, the long-term planning, the future planning year 3 to year 10, where we have honestly not much information. That's where the early engagement from the customer information could really help us to refine our forecasting assumptions. So on the right, what you can see is Electrification Early Customer Insight Project. This is a project that we're doing in the back office, really trying to bring a lot of data to a Snowflake database where we're really trying to, integrate a lot of different databases. For example, the telematics data from some of the manufacturer, like OEMs, Daimler, Volvo, Apple. Then we also bring the early customer insight from different organizations that are customer facing. We have multiple customer facing groups. They all have their different customer insight. For example, we have LPA that deals with government. We have we have CD account manager, which deals with large customer. We have e-mobility business operation team, which is really kind of partnering with the program folks working with the key customer. And then we have a Rule 2019 that's a very dedicated EV project team. Every team has those early insight. Currently, we're not tracking in the same database. So this is really intending to integrate those data in a central database and trying to make sense of all the early customer insight information. Well, this project also has the interesting AI web crawling component, really trying to do a daily AI web crawling to bring the external announcement. For example, if a company made an announcement on their sustainability plan, or if a national-wide fleet, they make a national, that's where we want to capture that and bring that information back just in case our customer-facing group doesn't capture that information. So we're integrating that information in really doing a lot of data analytics, and the end result of that is really informing the pending load assumption. All right, so last one that I wanted to highlight is, in addition to the traditional utility solutions, there are cases that we're already running challenges that capacity, the circuit could be running out of capacity and we couldn't really provide timely energization to the customer. So we're looking at a suite of bridging solutions to offer to the customer. The first one is a load control management system. This is a system where we will be sending the customer signals. The customer will have an option to participate. Currently, it's a pilot, so file an advice letter to the CPUC. The pilot will be running for 2 years. Once the standard is approved, we do imagine this process will go much smoother because today we have to do a lot of certification at SC ourselves due to the lack of standard. So the lead time for taking this customer going through this process can be taking a few months. But we're really hoping that can be really further down to helping the customer come online much quicker. We're also looking at relocatable storage and a mobile substation. So those are the solutions that we can put on our trailer, we're quickly deploy depending on where the grid needs are, where you can either put a customer premise or substation or along the right of way on some segment of the feeder. So those are the projects we identify need and include our general rate case. But this year, we're already moving forward, with the IFI, IP to start piloting. So with that, I'm going to conclude my presentation.
Thank you, June. Next up, we have Zach Pollock, who's the Director of Grid Strategy and Emerging Technologies with Xcel Energy.
Thanks, Matt. All right. Good afternoon. It's a pleasure to be here. You'll probably hear a lot of the same themes that you heard from June in my presentation, albeit with a little bit of a different take since Xcel Energy is a vertically integrated utility that operates in 8 states. We have all of the generation, the transmission, and the distribution planning functions in my organization. In addition to that, we're seeing many of the same drivers that California is starting to see, but we're addressing it from a few different perspectives. So just a little bit about Xcel. We serve about 3.8 million electric customers, primarily located in the Denver area in Colorado, along the I-70 corridor, as well as in Minnesota. We've also got a significant amount of load down in Texas and New Mexico. Interestingly enough, a lot of that is industrial and commercial load, largely driven by oil and gas, so a little bit of different customer profile there. Also, from an integrated perspective, we do serve a substantial amount of gas loads. So as we think about integrated planning, we're not just thinking about the electric side, but also how the gas side and some of the decarbonization mandates and goals that we have will impact our gas customers with that load coming over to the electric system potentially. We consider ourselves to be a leader in distributed energy resources. Between Colorado and Minnesota, we've got about 2 gigawatts of DERs on our system. In Colorado alone, we've got about 15% of our peak load coming from various distributed solar. Most folks know Xcel as being a leader in decarbonizing our generation supply. So I'm going to get to that on our next slide here. So we were, in our opinion, the first utility to come out with a net zero goal by 2050, and we're making significant headway on that. We have a goal to be 80% carbon free by 2030, well ahead of that in Colorado and parts of our other service territories, largely through a combination of wind and solar and nuclear, a little bit less so, and some of that up in Minnesota. And then we're also looking to do that on the gas service and being a facilitator of electric vehicles. So 25% lower is what we're aiming to get to for our gas emissions across the Xcel footprint, and then net zero by 2050. By 2030, from an electric vehicle facilitation perspective, we're looking to have 1 in 5 EVs be in our service territory in our state, and then have zero carbon fuel accessible within 1 mile by 2050. So in the context of distribution planning, I always think it's important to start with understanding where we've come from to understand where we're going and why this feels so different. If you think back to about 100 years ago, not even 100 years ago, large parts of America were not yet electrified. There was a national imperative to build out infrastructure to do that. And that's largely what you saw on the left side of the slide here in the 1930s and 1940s, as people started to recognize the importance of getting access to electricity. That era of load growth and infrastructure largely persisted through the 1960s, arguably. People started to get air conditioners, they get refrigerators, televisions a little bit later on. And that ushered us into the era of conservation and efficiency as we started to have energy crises, big focus on conserving energy. That focus on conservation, I would argue, largely persisted into the early 2000s and the 2010s, where folks started to recognize the impact of climate change and the importance of decarbonization. You saw that manifested in early renewable portfolio standards that have now shifted to be on broader decarbonization of power generation emissions. And that's largely where we've lived in that bottom of the trough till today. The conversation has shifted substantially today. We're now at this inflection point where utilities are being asked to be the backbone of economy-wide decarbonization, and that requires a very, very different approach to planning. So why has that approach worked historically, and why does it need to change today? Well, for us as a vertically integrated utility, what that meant for us is we were prioritizing investments in the power generation sector because we owned a lot of that generation. We were contracting for PPAs for stuff we didn't own as part of a resource acquisition process. Capital is finite as a utility, so we spent capital or used capital to make those investments. That allowed us to be a national leader. As you can see in the top left quadrant here, we're at about 50% of our generation mix being carbon-free today. As I said previously in the other slide, we're trying to get to 100% net zero by 2050. So we've been that leader in leading the clean energy transition, but it's largely focused on the power generation sector. It hasn't focused on thinking about how we're going to use the rest of our system, our power delivery system, to facilitate decarbonization of other sectors of the economy. So thinking what that means really comes down to the last sentence here. We need to move to a framework where we're doing more expedient, proactive, and transparent grid planning to meeting those new expectations on the distribution system as our customers start to use energy in new and different ways. One of the reasons it's worked historically is because we've been successful at conservation programs. So what you're seeing here, this is from Colorado specifically, but we kind of have a two-frontier problem, right? We've got customers that are using energy in new ways, and we've also got customers through economic development and new growth that are being added to our system. So the blue line represents additional customer growth that's accounting for additional sales. The black line represents per capita energy consumption for residential customers. So while we've been successful in reducing energy consumption on an individual basis, we're still seeing additional upward pressure on the system just from an energy perspective by adding those new customers. And what this doesn't show is layering in the impact of adding additional load from new uses of the system. So it goes without saying, we're seeing a massive transformation in how we think about the grid. It's no longer just this unidirectional flow of power down from generation to transmission to distribution. It's much more, in our view, sort of this grid architecture where we need to think about how planning across all the silos that have existed independently of another will interact. And that's largely why my organization, my leadership, has stood up the integrated system planning organization inside of Xcel. So just thinking about what the future could look like from a typical residential customer, today we're seeing about 6.97 megawatt hours per year of residential consumption. Obviously, this is on an energy basis, not a demand basis. But as you start to think about a customer adding a cold climate heat pump to serve the cold temperatures we have in Colorado and Minnesota, 8-9 kW load there, heat pump water heater, another 4 to 5 kW, first EV, second EV, you can start to see how the throughput of the system, both on an energy and demand basis, is going to increase substantially. So it goes without saying there's going to be need for significant investment in the system in a new way that doesn't conform with how we've done things historically. And it's going to be distributed in a very heterogeneous manner. So this is just an indicative illustration of some early analysis we've done, just showing some communities in the outlying Denver area where you can see from a distribution planning perspective, significantly different impacts on feeders depending on where it's located, what the customer demographics are. And that really gets to the challenge of integrated planning from a distribution perspective. We're not just planning for coincident system peak where you've got one planning objective that you're basically trying to hit from a reliability and affordability perspective. We've got 800 circuits in Colorado, and each one of those its own unique challenge. So a little bit of a representative of that from Colorado. This is exactly the same picture. I was kind enough to steal it from Reddit, but looking exactly at the same spot. You can see the massive amount of infill really in that sort of brownfield area abutting the park there. That is just over the last 19 years. So we're seeing a lot of that in terms of single family homes being scraped, putting up multifamily units. Then we've had historical arrangements that have worked well in the past, like automatic throwover and redundant feeders that customers, typically industrial customers or commercial customers, will ask for. Those are creating challenges because they're reserving capacity on adjacent feeders. So we can't serve new customers that want to come onto that or new expanded load growth as customers start to add new types of load. The last point here is that Colorado, while it's been a national leader in decarbonization policy, the policies for distributed generation largely have not evolved over the past 10 or 15 years. So we still have retail net metering for rooftop solar, albeit on time of use rates. We've got a fairly large community solar program, but that gives you the same value of compensation or bill credit, regardless of where you are on the system and what time of year or what time of day it is. So we think there's a lot of value in moving to a more constructive framework where DRs would be cited where they provide system value, given the massive amount of infrastructure that we think we're going to have to build out. So that's just where we are today. What does the future look like? There's a joke in Colorado that the state bird is actually the crane. You can count the number of cranes there. There's about 6 I can see, probably more I can't see. And then think about the urban development we're starting to see as we see more people wanting to move to Colorado as being an attractive place to work, live, et cetera. The photo or the rendering on the right here is from a development called River Mile. They've basically asked us for the equivalent of a small modular reactor of new load growth. So think about what that means from the previous slide here. Where are you going to put the substations to go support all of that load growth? And the short answer is developers don't want a substation in the middle of their multi-billion, if not larger development. So, and we're also seeing challenges from data centers. I mean, a lot of those are transmission connected, but definitely seeing some of that on the distribution system as well as a smaller scale. What does that look like? So these are our capacity checks. So when folks apply for service, there's what's called a conceptual capacity check. That's sort of the pre-formal application process. And then there's a formal load request. This is just reflecting the significant uptick we're seeing in Colorado. And again, to June's earlier slide, it's exponential growth. So how does this reflect itself in terms of challenges and impacts and potential solutions that we're seeing at Xcel? I'll walk through each one of these one by one. Really, the first one's sort of obvious, is the load growth is outpacing the historical adoption patterns that we've gotten used to. When we invested in the system historically, it was done in big chunks. So you go put in a 25 MVA or 50 MVA substation transformer, that would serve a lot of load for the next 10 years. That process today is not working. We've got to get out ahead of that and move towards a more proactive planning process. It also means that we need to be planning for individual customer adoption decisions. We can no longer wait for the load to show up. That is not an adequate solution. So it means getting comfortable with the uncertainty of planning for individual customer adoption decisions. And that really gets to the second point here. With that forward-looking forecasting process, we can't, as utilities, know exactly what a customer is going to do. Customers are not rational actors. They make investment decisions for a whole lot of reasons. There needs to be additional margin in the system so that when we're wrong on the forecast, and inevitably we will be wrong, we have the ability to absorb that in a way that doesn't deter our customers from connecting their new load or being able to serve them in a timely and affordable fashion. The third line here really talks to the nature of the distribution system and how it's been operated for the last 100 years. We've had pretty limited visibility into the system. It's largely been a connect the load or connect the generator and forget about it. That needs to be reconsidered as we have the technology and the processes available to think about planning the system more dynamically. So the term dynamic operating envelope gets thrown out there a lot, but thinking about how we can use technology to not plan and operate the system deterministically, and how we can do it in a more flexible, efficient manner. And then finally, there's a lot of priorities on the system. So historically, from a capacity planning perspective, the question was always, how big does the wire need to be? How big does the transformer need to be? We're trying to balance that, not with just how big does that need to be in the distribution system, but how does that relate to the amount of generation I'm investing in, our transmission planning needs, as well as other emerging needs like wildfire risk and other risks that we have on our system. So the question no longer is just how big does it need to be, but it's how big does it need to be? How can I meet resilience objectives, reliability objectives? And that's largely why Xcel has taken it upon itself to stand up an integrated planning group. So I'll talk a little bit more in detail about some of the things we're doing today, and I'm sure some of this will come up in the Q&A. Really talking about the highlighted things here. So how we're enhancing our forecasting process and how we're thinking about technology to more dynamically plan and operate the system. Obviously, these things occur over a spectrum. That's what's indicated by the chevrons here. So talk through each one of these. Really, all this is tied together by our vision for the grid of the future. Very similar to what June described with some of the industry-leading work that Southern California Edison's been doing. Given the uncertainty I was describing, we think there's significant amount of value. Ooh. I'm getting a Zoom issue here. Nothing like a random dialog box. So we think there's a significant amount of value in doing scenario planning to account for that uncertainty of those customer adoption decisions, as well as the rapid pace of load that we're seeing on our system. So our view for the vision of the grid of the future starts with that scenario planning process. That largely assumes the system is going to be planned and operated the same way we've done it for 100 years. So we think there's also significant value in running sensitivities. What does that look like? So thinking about some of those flexible and dynamic loads, the secret sauce, right, is we all recognize there's a significant amount of infrastructure that we're going to need to invest in. How do you do that in an affordable way? And that really comes down to the simple utility cost of service, right? So if you can take your fixed costs and spread them out over more kilowatt hours, then you can help mitigate some of the upward rate pressure. And that's where we think the ability to model sensitivities around things like EV managed charging, flexible load connections, et cetera, comes into play. The third piece of this is something that we think is a little bit unique and special that we've added to the discussion here. Is the challenge for my leadership is to understand how we're going to build the system. So the last part of this is thinking about design basis. The challenge from my leadership is to think about how we're not going to invest for the next 5 or 10 years, but think about what the challenges and the opportunities are for the grid over the next 30 years. And we're doing that through thinking about standardized design basis in terms of how we design feeders, substations, et cetera. So there's longevity in those designs. So we're not planning for that 5 to 10 year horizon that we've been accustomed to over the last, I would say, 100 years or so. So what does that look like from a modeling perspective? Historically, the way we've planned the system is we've identified budget, and we've done as many projects we can do to serve load. That fundamentally needs to change, and that feeds into the scenario modeling that we're starting to do here. We think one of the things that we're trying to accomplish with our Grid of the Future initiative is to really have a fact-based conversation with our regulators and our policymakers. There's been aggressive goals in Colorado, mandates in some cases, without necessarily a full understanding of the facts, because no one's taken it upon themselves to do that modeling. So we feel it's imperative to have this scenario-based modeling framework that just identifies and allows us to have a fact-based conversation with our policymakers and our customers so that they can make the best informed decisions that they can. So obviously there's other things outside of capacity growth on the distribution system. Some of those things are reflected in the last column here in terms of other generation transmission planning and non-capacity drivers like wildfire, asset health, and reliability. Those are all important categories too, but I think the conversation today we're here talking about is really more on the capacity side. From an enhanced forecasting perspective, to get to some of that customer adoption propensity, we've adopted a few different tools. The one here represented is a software called LoadSeer that allows us to take the top-down forecast that you heard June describe earlier and do a spatial allocation so we can understand on an 8760 or hourly basis what the load impacts are going to be in aggregate of not just load, but also thinking about distributed generation, electric vehicles, et cetera, we have to be able to understand the coincidence of all those loads at a distribution circuit level, at a substation transformer level, and arguably at a service transformer level. So that's one way that we're starting to do this. We're also exploring the use of machine learning to better inform those customer propensity adoption. So this is an example here of some early work we're doing around solar adoption. You can see the variables and predictive indicators that we have on the right here. Those are some of the things that we're seeing some predictive power in terms of the model that's been stood up to be able to do that. And then the last slide here really talks about that more dynamic management of the grid. So thank you to EPRI for this slide, which tries to illustrate how flexible interconnection works. But today, or historically, we've managed the system to deterministic limits. This is really indicating that if you're able to identify through more sophisticated and robust analysis, typically through time series like an 8760, you can actually manage the grid more dynamically. We're seeing that largely as one of the key use cases for our DERMS roadmap, as we start to think about how we can integrate DERMS with our advanced distribution management system and SCADA and other tools that give us operational visibility. But more critically, from a customer perspective, it gives us the ability to potentially bring on customers faster in a more affordable way as we're waiting to build out the infrastructure, because we're not going to be able to build the infrastructure we need in all cases. So we're exploring that capability. And then the last point here in my last 5 seconds is that the regulatory constructs and tariffs will also need to keep up with the changing capabilities of technologies to be able to fully realize the value of this. So last slide there. Right on time.
Great, thank you. Thanks, Zach. Wow, there's a lot going on in those two utilities, some really forward-looking planning. So I'm looking forward to discussion around those. We're going to shift gears a little bit to some particular approaches and tools to dealing with this same issue. And welcome Chelsea Petrenko, who's the Associate Director with Energy and Environmental Economics.
Good morning, everybody, or good afternoon. Today I'll be talking about geospatial forecasting of electrification load and effects on the T&D system. There's a lot of overlap here with the first two presentations you heard, and so it is exciting that we're all thinking about the same things and heading in the same direction here. So just a little bit of context on who E3 is. We are an economic consultancy focused entirely on the transition to clean energy resources. And our research spans many different topic areas, ranging from economy-wide energy systems, things like pathways to decarbonization, which is my area of focus, to researching bulk grid power systems, and then all the way on the right here, grid edge and behind the meter topics as well. So the big picture challenge, as June and Zach have already touched on, is that as we are rapidly transitioning the grid, planners must simultaneously understand this picture at a very large scale in terms of planning for decarbonizing electricity, electrifying transportation and buildings, and doing all of this while maintaining a reliable, safe, and affordable grid. And then they're also grappling with the very fine scale challenges of local updates and infrastructure upgrades needed for feeders, incentivizations to adopt heat pumps, and make-ready programs for TE. So there's a lot going on, and oftentimes these large-scale and local-scale dynamics are not necessarily being connected. So some of the specific challenges that we're hearing, and we've already heard a bunch of these today, one big one is the magnitude and timing of new infrastructure need as it relates to new load coming onto the grid. There's also an interest in comparing costs of alternative net zero pathways. There's a need for anticipating customer interconnection, and not just with data centers, but with medium heavy duty vehicles is a big one that we're focused on and is a topic of this presentation today. Utilities are grappling with translating these state clean energy goals to local infrastructure needs. We're also looking to visualize the impacts for planners and stakeholders. So you can have a lot of information and a lot of data, but it's very helpful to actually be able to visualize these things and get that out there so that you have the support you need to be able to make upgrades and make the case for that. In terms of more practical purposes, utilities are asking, how do we prioritize feeder upgrades? Can you tell us the top 10 feeders that we're going to need to upgrade in the next 5 years? Is there a substation that's going to be overloaded in the next 5 years? And then lastly, where will adoption happen with and without public policy and funding? So this relates specifically to funding in disadvantaged communities. If we are investing more with things like Justice 40 initiative, how will that actually affect the propensity for adoption of electric devices in different locations? So in terms of big picture solutions, E3 is really focused on integrated system planning, which aims to unify planning across all parts of the system and arrive at better solutions that are taking into account the whole system. I'm not going to go into this too much today because that's not the focus, but I'd be remiss if I didn't mention it because it's a huge part of the solution here. And our model that I'll be talking about today kind of sits at the seam of distribution planning and distributed resource planning. And that specific solution is geospatial forecasting of DERs. So what we're doing is translating economy-wide decarbonization plans to geospatially explicit expectations of DERs and electric devices, including EVs, heat pumps, and distributed generation. So we start with planning scenarios such as pathways to decarbonization scenarios. They're informed by policy, macroeconomics, and technology drivers. We take those economy-wide planning scenarios and we translate those into geospatial DER adoption and load growth scenarios. We do this using machine learning and heuristic analysis where there isn't historical data to train a model on. And this comes up a lot with the medium heavy duty TE space, since that's really just at the beginning stages of electrifying. So forecasting anywhere gives us a lot of outputs that ideally we can work directly with distribution planning software to analyze and look at a grid level. Specifically, we work with LoadSeer a lot because Integral Analytics is a sister company of ours. So we've developed a lot of these processes together, and we've had some really interesting projects working with utilities where we're able to get our forecasting results that are based on planning scenarios and then apply those directly to their distribution planning software. This geospatial forecasting of DERs helps solve some critical shortcomings of current distribution planning norms. It provides a quicker, diversified set of results instead of one planning scenario that can take months just to develop that one scenario. It anticipates needed infrastructure upgrades so that the distribution doesn't become the bottleneck for achieving transportation and building electrification goals. It offers more precise plans as demands on the distribution grid and planners are growing and starting to include a lot of different diverse aspects like wildfire risk and resiliency. And it gives utilities a convincing case to regulators and stakeholders that their preferred distribution plan is prioritizing the right investments. And this is a big one when we're working with utilities. They want data and information and proof when they make their rate cases that they need to include these different investments in infrastructure. So I'm going to go over the forecasting anywhere workflow. I think it's important to understand how the model works. It gives an idea of actually what we're doing here. So first we determine technical potential, and this is on a parcel by parcel basis. So it's very fine grained. We're looking at what is on every parcel, whether it's a business, parking lot, residence. And this gives us the number of chargers that you could deploy in a certain jurisdiction. For example, if we're looking at building electrification, we would be looking at square footage. Next, we calculate propensity or the likelihood to adopt whatever device we're looking at. This takes into account lots of other variables, and Zach had listed a bunch of those that we use typically to predict propensity to adopt, things like the size of the home, income, various other aspects. This score is on a 0 to 1. And if you're in a jurisdiction where they're trying to reach 100% electrification to reach decarbonization, then it's not necessarily a matter of if a parcel will adopt, but when. So parcels with lower propensity scores will end up adopting EVs and heat pumps. It will be closer to 2050. So that's kind of how that works. Then we determine the local level adoption. So this relates to what I was just saying. So it's like the number of devices that you would expect in a jurisdiction based on those overall economy-wide goals. Then we geospatially aggregate those devices based on the propensity scores. And finally, we're calculating load impacts. So this is where sensitivities on load shapes and demand side management strategies come into play. So it's one thing to kind of distribute the devices across the territory, but then we're translating that into actual load impacts, which can vary a lot depending on if there's time of use rates or other types of programs to incentivize shifting load off peak. And finally, we're producing data reports and visualizations that are used in a number of ways. And as I mentioned, ideally go straight into distribution planning software. So a couple key modeling elements. One is designing effective scenarios. Strategic scenario design allows planners to look at a diverse number of variables that may change between now and 2050. So it's important to consider not just one future, but look across a number of possible futures. And then it helps planners decide, okay, under all of these futures, it makes sense to take A, B, and C steps. So let's do that. So we find this to be a very effective approach with both decarbonization planning and this forecasting anywhere work. Possible levers that we've been using are different EV and building electrification adoption trajectories, different load management strategies, emerging high demand technologies such as high powered charging, specifically in the medium heavy duty space, and investment in low income and disadvantaged communities. So one of the things we can do is assume that more money is flowing into disadvantaged communities and see if that shifts adoption geospatially into those areas. The bottom right GIFs here are showing adoption of building electrification devices, aka heat pumps, and EVs over time in the 5 boroughs of Manhattan, based on a few different scenarios that we ran for them. A second critical element is collecting a lot of geospatial information for whatever jurisdiction we're conducting the research in. So I won't go over all of this, but one critical thing is understanding what's at every parcel. We use zoning information. We look at the value of properties, the size of properties. We look at business filings, NAICS codes. We're trying to determine if a business has a fleet in a certain location, and if so, how many vehicles would be in that fleet. I think Jude mentioned that's very difficult data to find. So there's a lot that goes into the data gathering step. We create custom EV charging load shapes using our Reshape EV model, which is based on driving patterns of thousands of drivers and characteristics of the driving population. And then we can create lots of different types of shapes based on different time of use rates or demand management programs like off-peak charging programs, and create various different sensitivities that we would test. And then we do the same thing for building load shapes. So we have a model called BuildStock, which is based on NREL's ResStock and CompStock building simulation tools. And here, similar concept of pulling various different levers to look at how that would affect diversified building loads. Some of the key ones are whether we're using high efficiency or standard efficiency heat pumps, and different assumptions on weatherization of buildings. So I would like to share some findings from a few of the public studies that we've done. In 2022, we worked with the LIFT to understand how investing in disadvantaged communities would affect adoption across California. California was considering a tax that would support EV infrastructure. And what we found was that by shifting this funding into disadvantaged communities, we could add over 7 million chargers in those locations. It's largely in the Central Valley there, the yellow part in the figure on the right. We also found that by funding in these communities, charger distribution shifts to lower income in terms of the income levels of homes. So with business as usual, household income less than $75,000 had lower charger adoption, but with this extra incentivization, there is actually more adoption at those locations, according to our model. Shifting coasts here, we helped New York City with their Power Up NYC initiative, which is a climate plan that they do every 4 years. One of their questions on a practical level was, where are New Yorkers going to be getting EVs and where should we put our public chargers, both L2 chargers and DC fast chargers, because they have goals for both of those. So we were trying to help them figure that out. They were also curious where their grid would need upgrades. And for that piece of it, we worked with Con Ed. We weren't able to get specific feeder level data, but they gave us planning distribution area data. So we were able to identify areas that do not have enough headroom in the long term. So the top blue figures here are building electrification and transportation electrification, adoption expectations till 2040. And then on the bottom, we were looking at unmanaged load shapes versus managed load shapes. And you can see out in 2040, the bottom right figure, there are higher impacts out in 2040 out in the outer reaches of the boroughs. But with managed charging, that alleviated some of that. And then in terms of headroom on the system, we found that like Bronx and Queens areas and parts of Staten Island were going to experience some issues out toward mid-century, which is something that Con Ed had on their radar. What they didn't have so much on their radar was actually in downtown Manhattan. So we went into it with them saying, like, we've overbuilt the system in downtown. We anticipated a lot of load, not necessarily from decarbonization, but long ago, they were overbuilding the system. But even that wasn't quite enough. Downtown Manhattan is, well, I don't have the pointer, but it's red in this figure. So last study I'll go over is NV Energy Integrated Resource Planning, which we just wrapped up with them. So they were curious in testing a number of different scenarios and sensitivities and understanding how demand side management strategies impact the grid. So we designed several different scenarios and ran pathways for them. We looked at 3 different distinct demand side management portfolio designs, ranging from your kind of classic demand side management strategies to more aggressive things. And we also did an assessment of impacts on low-income communities under different scenarios. And this figure on the right is showing the chargers installed around the Las Vegas area. And I just wanted to point out one interesting thing that we're seeing here and other places is that we see a lot of this kind of red level chargers installed, which then translates to higher load impacts on the outskirts of cities, which are typically L2 chargers in residential areas. And it's not necessarily, with clients, it's not always expected that where that's what's going to be driving the issue is L2 chargers in residential areas. We think about medium heavy duty a lot as these are kind of point sources of very high demand, but altogether L2 adds a lot of load onto the grid. And these are sometimes in areas where they just weren't planning for this high of demand in certain like residential areas. So it is helping clients hone in and kind of shift focus to areas that might need it more. Another jurisdiction that we were working in, or that we're continuing to work in now and just getting findings, they anticipated medium heavy duty and commercial charging to really be the problem going forward. But what we found is that because the commercial areas are actually distributed pretty well across the city, their grid can absorb that load pretty well out to 2050, but their residential areas actually are going to need some help. So how can we improve the modeling? We're always actively working to answer new questions and improve our model. One thing that is great is when we can coordinate between our research and utilities and state level planners. When you have that feeder level data, it allows for much more granular predictions of upgrades that need to be made. So it's always great when we have that. One is incorporating vehicle trip data to strengthen and ground truth several aspects of the model, including verifying charger locations and verifying charging load shapes. We're looking to gain insight into how the medium and heavy duty sectors are evolving. So this is one of the areas where I mentioned there's not a lot of historic data to train models on. And we basically annually have to go back and see which class vehicles are coming out and work with partners who specialize in this sector to understand how we predict these types of vehicles and fleets electrifying. We're doing more detailed assessments of how investing in disadvantaged communities impacts adoption. Obviously, funding is one key element which we can capture in the model, but it's harder to capture qualitative barriers to adoption. And so we're trying to figure out ways that we can have our model incorporate those. We're also looking for higher temporal resolution and granularity in load shapes, and specifically the ability to change load management assumptions over time. We do think that as we approach 2050, load management will become the norm, but it's definitely not the norm today. It's actually lower than you might think based on early evaluations. And so this is one way that we're trying to improve our model currently. And we're looking for granular building electrification data. So it can be surprising if you're working with an electric only utility who doesn't have insight into the gas system and customers in their territory. They actually don't have great insight into who exactly might get off the gas system and adopt a heat pump and then become an electric customer adding to winter load. And so this is a problem. So we're trying to figure that out. And also we're generating rapid high level distribution planning area costs and impacts. So cost is always a key driver with all of these studies. We're trying to translate the findings here into predictions of costs. And that's all I have today. Thank you very much.
Great. Thank you, Chelsea. For our last presentation, today is from Nick Miller. Nick was, like our other panelists, enthusiastic about being here today, but due to reasons beyond his control, he was unable to attend. And we're really appreciative to Debbie Liu, Associate Director of ESIG, for stepping in on short notice to deliver Nick's presentation. Thanks, Debbie.
Thanks, Matt. So yeah, today I'm going to do my very best imitation of Nick Miller. This is going to be really, really fun. Yeah, you're asking why am I here? It's because we have this building electrification task force. It's looking at building electrification, especially heat pumps. PEI is the subject of this talk, and we have been learning as much as we can in this task force about what's been going on with PEI. So strange case of Prince Edward Island, PEI, perfect storm for heating electrification. This is not just Nick, but also Scott Harper and Marianne Rogers from WACAN, the Wind Energy Institute of Canada. So I'm going to basically explain the island system, talk about how they've encouraged electrification, talk about this perfect storm idea that stressed the system, and tail events, including the polar vortex, and talk about whether this is a canary in the coal mine. And this is part one of a story. So if you want to hear part two, you got to come to the ESIG Fall Workshop in Providence in October to hear part two, where we're hoping to get the Canadians to come and give that. So for those of you who don't know, Prince Edward Island, small island up in the northeast. So yeah, the pointer is really difficult to do from here because of the angle, but you know, it's part of the Eastern Interconnection, part of the Northeast Power Coordinating Council, and it's tiny, 100,000 customers. It's made up of Maritime Electric and the city of Summerside. And this sort of shows you the system, Prince Edward Island being that little kind of blue in the left-hand figure, the lighter blue. And you can see it's basically got a single tie line cable, 230 kV single tie line to New Brunswick. It's a winter peaking system, as you can imagine. They got some wind on it, and the right-hand graphic here is showing how good of a wind resource. It's a really nice wind resource. It's got some fossil generation. They've got a heavy reliance on this little 230 kV intertie. And in 2022, Sargent and Lundy were commissioned to run a capacity resource study. And capacity obligation in 2023 was set to be at 311 megawatts, basically reflecting a planning reserve margin of 20%. And this top table is showing what makes up that 311 megawatts of capacity obligation. So it's comprised of on-island combustion turbines, 89 megawatts of on-island CTs that rarely run. They're expensive, they rarely run. There's 93 megawatts of nameplate wind on the island, but when you calculate the capacity value of that wind, it's 21 megawatts of effective load carrying capability. And then they own part of a nuclear station that's not on the island. So 29 megawatts is their share of what they own of that. And that power they bring through that intertie. And then they also do short-term capacity purchases from New Brunswick. So 172 megawatts of purchases from New Brunswick across that intertie again. And this capacity resource study found that they should install a new 85 megawatt fossil fueled power plant. It would run at a relatively low capacity factor. As you can imagine, it's a big resource for this size system. It's pretty expensive. And that's going to be the focus of part 2 of this in the fall. But that was the recommendation coming out of this study process, looking at their resource planning. The way they run their system is that, so here you've got the nukes in blue. So that 29 megawatts, is running flat out all the time. They're bringing that across the intertie. And then in green, you can see the wind plant. So whatever wind they generate, they're using. And then they make up the rest of it. Basically, they balance the system through these purchases from New Brunswick. And that's the orange here. So there's not a lot, again, of on-island resources are expensive. So they're really heavily dependent on this intertie. If they lose that cable during peak load, they can't serve load, right? But, this only happens, say, once a decade. So, they're basically meeting their criteria, okay. Now, Prince Edward Island also has ambitious carbon targets. So they want to be net zero by 2040. And you can see here that one of the things they've done to incentivize their customers to reach these carbon targets is to have a free heat pump program. So you can see here, if your household income is $100,000 or less, you could be eligible for a free heat pump in 2024. And this heat pump program has been going on for a while. So, first it started with $35,000 less threshold, then it went up to 55, then went to 75K, and now it's at 100K. But you can see over all this time, people have been signing up for heat pumps. They've been getting free heat pumps. They've already got 3,000 heat pumps installed since 2021, with another 7,000 installations that should have happened already, right? So there's a lot of heat pumps going on, and they're continuing to incentivize and give out free heat pumps. So this trend of heat pump growth is planning to go on longer. And these heat pumps, they're small air source mini splits that are mostly being installed. And another piece of this puzzle is that heating oil prices have been going up. So in 2022, you can see, where that green arrow is, that oil prices went up a factor of 5 compared to what they were back in the COVID times. And that's been helping folks to do fuel switching from oil to electricity. So that's been also encouraging people to move to heat pumps. And it's not just heat pumps. They've also got solar incentives, electric vehicle programs, level 2 chargers that they're incentivizing. So there are other things that are going on in addition. And I think you'll probably hear about this in the fall as well. But the event I want to talk about is February 2023. So there are people in the audience who know way more about polar vortices than I do, but basically, usually we've got this stable polar vortex. It kind of keeps that cold mass of low pressure cold air up in the Arctic contained. And when it's unstable, the cold air moves farther down south. And so that's what happened during this event, February 3rd through 5th. And I know you can't see it because the numbers are so tiny, but on the right-hand graphic, those temperatures, are going down to like minus 41C, which is coincidentally like minus 41F. So it's like where Celsius and Fahrenheit sort of cross over. So it's really, really cold during this cold snap. And this is just sort of talking more about the temperatures and the wind chill factor. But basically, the top right is showing all of February. And you can see that blip, February 3rd through the 5th, where temperatures really dropped down. Now, I should ask, who's got a heat pump here? Anybody have a heat pump? Oh, a lot of people have heat pumps. Oh, okay. All right. So great. So you guys all know. For those of you who don't know a lot about heat pumps, they can heat, they can cool. When they heat, it's like running your air conditioner backwards, right? They're moving heat from the outside to the inside, and they're very efficient, right? But when it gets very cold, they get much, much less efficient. And so because of this, and maybe I should ask that too, do people have supplemental backup heat on their heat pumps? Yeah, some people do. All right, so when it gets really, really cold and they're much less efficient, they often have gas or resistance backup heat, a supplemental source of heat. And in PEI, they had resistance heat as a supplemental source. And this bottom left graphic is from New York ISO, but it gives you a sense of what the supplemental heat source can look like. So this is just showing for a house in New York, the heat pump load is the blue part that goes up to about 6 kilowatts for this particular house. And you can see that when it gets really cold, especially at the beginning of this period in like January, the first week of January, you can see that there's a resistance supplemental heat kicking in, and that can be about 11 kilowatts extra, right? So, you can think that your heat pump load is only 6 kilowatts, but when it gets really cold, it might be kicking in that resistance supplemental heat, and your load might be tripling, right? So that's something that can take planners by surprise. And depending on the climate, these cold events could be really rare. You might not even know that your building's got this backup resistance heat until a cold snap happens, and then that heating demand triples. So, so that can be an issue. And that's essentially what was happening here in Prince Edward Island. Basically, load peaked at 396 megawatts, which is about 23% higher than last year's load peak, which was also a record peak. So the record peak went up a huge amount in 1 year. And then, remember that I showed an earlier graphic from the capacity resource study that was done by the consultant, where we had talked about a 311 megawatt capacity obligation, right? So this is 396 megawatts. This is, much higher than what they thought. And the other thing that's really important here is that if you look at, so that dashed line is the previous record load from the previous year. And if you look at where the red line, which is the load, crosses the dashed line, you can see that once they broke that record, the load stayed higher than the previous peak for 27 of the next 31 hours, right? So this was a long event. And this reinforces something that, we talk about a lot here at ESIG. And that's that, summer peak, your summer peaking system, summer peak is generally a pretty short duration event. You can have a battery, you can have demand response that can help you get through this. But with winter peaking events, if you're talking about, 27 of these 31 hours, that's a lot to get through on a battery or on demand response. And those might not be sufficient enough to deal with long winter peaking events. So, okay, they did get through this event. There was no load shedding. And how did they do it? So they got by with a little help from their friends. On the top right, this is showing that they had some wind. That's in green. And they ran their on-island fossil generation. I'd mentioned, it's a little expensive. They don't run it much. That's in blue. That's on top. They ran, looks like about 80 megawatts of that. It was hard for me. I'm just eyeballing it. And they've got 89 megawatt nameplate capacity of that. And then they maxed out their tie line, right? So that's in pink. The pink is their tie line from New Brunswick. Way exceeded their normal maximum. I'm eyeballing 280 megawatts imported across that tie line. And what you can see on the bottom left graphic that you probably can't really read because the print is a little small here, but basically Quebec was really tight. New Brunswick was really tight. Both Quebec and New Brunswick are declaring energy emergency alert level 2, right? So you get to level 3, you are load shedding, right? So this is level 2. They're like, getting towards that, but not yet load shedding. So Quebec and New Brunswick are in trouble. Quebec actually curtailed their exports to New Brunswick and was purchasing a gigawatt from ISO New England. New Brunswick was purchasing 400 megawatts from ISO New England. You can't really see it on this map because I've covered it up, but on the top right, there's Newfoundland. And Newfoundland actually was a little bit warmer. And so they were able to send 250 megawatts to Nova Scotia, and then that was able to go through Rhode Island. So the reports from the Sargent and Lundy folks, they report that PEI avoided load shed by like a handful of megawatts. So it was a really tight event for them to get through. Some of you might be asking what happened with the wind, because you can see here that the wind is pretty low and getting lower throughout that event. And basically only about a quarter of the wind turbine generators were operational during the cold snap. Some wind turbines were tripping on turbulence. And then, so what happens is they trip on turbulence and then they're going to restart, but it got so cold, the lubrication kind of froze up and then they couldn't restart. So they just kind of got stuck there, tripped. So lubrication is an issue because, wind speeds were pretty good. And you can see the wind tripped down on turbulence and basically couldn't get back going again. They also tripped out on low voltage lockouts. This is kind of interesting. They would trip for issues due to lubrication, but because the wind is kind of at the end of a radial line, the act of them tripping reduces the voltage, and then they couldn't start because voltage was low. So it was kind of unfortunate. All right, so forecasting, was there a forecasting problem? If you look at their forecasting, it's been reasonably accurate. So their projected peak is the blue dashed line. And their actual peak is the gray dots. So you can see that, generally they've been pretty good at meeting their projections, and that particular year, 2023, was an outlier. Now, if you kind of look at what happened and kind of let's see what happened with respect to temperature and what happened with respect to heat pumps and what happened with respect to peak demand. So we've got temperature, or the purple dots here, and this is showing the minimum temperature for each of the years. The heat pump growth is the orange dots here. So you can see heat pumps are growing, steadily, and there is a bit of a bigger jump in that 2022 to 2023. But the growth in peak demand has also been steadily increasing, but there is a major jump from 2022 to 2023. And so it seems like the main driver is really the cold temperatures that caused all those heat pumps to go into resistance heating mode. And then that's what really drove that demand up by 23%. And, one of the things that we might consider is that, there's this lurking risk, right? So like, so when John Black of ISO New England is forecasting load for, this cold climate, do you know if your heat pumps have supplemental backup? I mean, do we know if the heat pumps have gas backup or electric backup? Sometimes it's hard to know all of this about a facility. And maybe if you haven't gotten cold enough for a couple of years to trigger that supplemental heat, it's possible you can get lulled into thinking, oh, everything's fine. And then you get a cold snap and then this happens. So it's something we need to really think about and consider in the future. Just a couple other real quick things. NERC issued a level 3 essential action alert on cold weather preparations. Basically, level 3 is the highest severity level that NERC issues. And it's also the first time that NERC ever issued a level 3 alert. But, NERC was basically noting freezing conditions remain a reliability for generators. I think we need to consider how the demand side also plays into that. Another quick note from Nick is that we got to worry about what happens when you've got a whole bunch of your load that's of a relatively homogeneous character. So is there some common mode operational performance thing that could happen when you've got a lot of aggregated one type of load? Like a ride through issue that could potentially happen if you've got a lot of stuff that trips offline in a common mode manner during a fault event that could cause frequency issues. So there are other things we should think about. What did we learn from all this? You know, basically we need to really think about more granular long-term load forecasting, understanding the characteristics of your loads. You know, do you have a cold climate heat pump? Those might not require supplemental backup heat sources, for example. You know, we need better coordination with, you know, the policy people who are doing the incentives and the electricity people who are planning the system. We need to understand extreme weather events better, how those are going to evolve in the future, of course. And then finally, you know, there's parallels here with weather-dependent forced outage rates. It's kind of the opposite here because it's a load issue, but just, you know, any kind of common mode issue with, you know, lots of homogeneous character of a device can be important to consider. So if you're interested in this, come to Providence and hear about part 2 of the story in October. Thanks.